Hello everyone, and welcome to our class video about differentiability in piecewise functions. Our learning goal is that you will be able to determine and justify whether a piecewise function is differentiable. Wow, that's a big word there, you're probably thinking. What do you mean differentiability? Well, let me help you break it down. We say that if a function's derivative at x exists, then that function is differentiable at x. So differentiable just means that the derivative exists there. So let me show you where this word comes from. The word derivative is the noun that we've been using thus far to describe the slope of the tangent line and the instantaneous rate of change of a function. The verb form of derivative is differentiate, which means to take the derivative. It also means outside of math to tell the difference between, but we're not worried about that right now. If we add the suffix able, then we get differentiable. Okay? Then if we take that word and change it back to a noun, we would get differentiability, which is a state of being. So it's kind of like you could describe your car as whether a car is drivable or not. Okay? Whether it's able to be driven. Then we could talk about the drivability of the car. Sounds kind of weird still, but that would be the state of being, whether it's able to be driven or not. Okay? Help you make it understand a little bit? I hope so. So let's just see, how can we determine whether that derivative exists or not? Differentiability is really closely connected to continuity. Continuity has a certain number of conditions, and differentiability has a number of conditions required in order for it to be differentiable also. Okay, so do y'all remember how many conditions continuity has? It's 3. Differentiability, on the other hand, has 2 conditions, although you can really count it as 4 depending on how you count it, but whatever. Okay, so let's look and see what those conditions are. We've already talked about previously in class the conditions for continuity. Do you remember what they are? Pause the video real quick and see if you can get those conditions down. Then start up again and see if you got it right. Alright, let's see. The first condition is that the function value at a exists. A is just the value of x that we're interested in, analyzing the function. So the function value must be defined at x equals a. The second condition is that the limit as x approaches a from the left on the function is equal to the limit as x approaches a on the right of that function. Okay, then the third one would be to say that the function value is equal to the limit value. A short way of putting all of this is to say that the function value exists, the limit exists, and they're equal to each other. We've already talked about that. If you need some help still on that, feel free to ask in class. Okay, now let's talk about what the additional conditions are for a function to be differentiable. The first condition is that the function must be continuous. Here's the reason why. Here's a discontinuous function. We have a jump discontinuity right there, which means at that value of x, it suddenly jumps from a negative value to a positive value over no horizontal space. That would be a rise of something divided by 0. Anything divided by 0 doesn't exist. Hence, the derivative wouldn't exist there. Okay, so that function is not continuous and would therefore not be differentiable. So what this means is that I need all 3 conditions of continuity to be true in order for a function to be differentiable. So if I need to know whether something's differentiable, I need to first check all the conditions of continuity. The second condition of differentiability is that the derivative on the left would have to be the same as the derivative on the right. Kind of like in condition number 2 on the other side. The function value, the limit of the function value is equal to the limit of the function value on the right, on the left and the right. You get what I mean. Okay, so the derivative on the left would be the limit as x approaches a from the left on the derivative. And the same on the right side, the limit as x approaches a from the right on the derivative. Okay, So the derivative on the left would have to be equal to the derivative on the right. Another way to put that would be to use our limit definition of a derivative. Okay, you all recognize that? Okay, the limit value of the average rate of change must be the same on the left and the right. Okay, so now that you've got that down, let's apply it to some individual questions. Okay, here's our first one. I'm going to walk through and model my thinking and kind of guide you through the process. I'm going to be applying the principle of RADAR, which is an acronym used for figuring out a word problem. If you don't remember, we should have talked about this already in class unless I've rearranged the order of things. RADAR stands for read, ask, decode, apply, and see whether your answer is reasonable. I'll walk you through those steps. First, I need to read the question and just get a basic picture. I don't have to understand it right then. I just need to read it to get the big picture. So the function asks, or the question asks, is f of x equal to the absolute value of x differentiable at x equals 0? And then it wants me to justify my answer. Okay, I've read the question. Ding. All right, now I need to look at what the question is asking for. The function asks me whether, why do I keep saying function? I don't know. The question asks me whether that function is differentiable or not. So I'm going to use the hashtag symbol to denote what the question is asking for. It's the main idea. It also asks me to justify my answer. So it's asking me two things. So I need to supply two things in my answer. But when I do the ask part of RADAR, I not only need to mark it on the question, but I need to write down a visual reminder of all the different things so I don't forget to finish the question. That would be awful, right? Okay, so I'm going to write down, I need to put a sentence to say whether it's differentiable or not. So I'm going to start a sentence and say f of x. I'm going to leave a blank, so either it is or is not differentiable at x equals 0. Okay, then because it wanted me to justify, I'm going to put because after that. Okay, so that's going to remind me, it's going to sit there and remind me that I need to fill that in whenever I'm done to make sure I've done all the parts of the question. Okay, I've finished the ask part, so let's decode. I'm going to go through the question slower now and see, and kind of change that into something that makes sense to me. First, the word is. That implies to me that it's a yes or no question. Okay, we kind of already got that part. My function is the absolute value function. I know that. The absolute value function, by the way, this is an aside, is one of the most basic piecewise functions and one of the most common because for x less than 0, it's defined as y equals negative x, and for x greater than or equal to 0, it's defined as y equals positive x. Differentiable is a key math word, so I'm going to circle it. And that's an indicator because I want to know if it's differentiable, I need to check all these conditions. So I'm going to go ahead and draw the table right now. Okay, as soon as you see that word is differentiable, bam, you want to draw this table. Okay, if it's asking if it's differentiable. So that way you can check you remember, you go ahead and write down the 1, 2, 3 and the 1, 2, so you remember to check all the conditions. Just get in the habit of drawing that every single time. Then x equals 0 is the x value I'm interested in. Alright, so I think I've decoded that. So I'm done with that part. Now let's apply our understanding. The first condition I need to check is whether the function value exists. So pause the video real quick. I'll give you lots of opportunities to pause here, so be ready. Pause and see, do you agree that f of 0 exists or not? Yes, it does exist. The function value at 0 is 0. Alright, great. We need to check the second condition now, which is that the limit exists. So I need to see if the limit as x approaches 0 of f of x is the same on the left and on the right. Pause the video real quick and see if you agree. Well, yes, that limit does exist because on the left side, the function value is approaching 0. On the right side, the function value is approaching 0, so they're approaching the same value. We're good. The last condition is to say whether those two values are equal to each other. What do you think? Why, yes. Those two are both equal to 0. The function value is 0 and the limit is approaching 0. So there we go. Or I should say the limit of the function is approaching 0. There we go. Okay, so now let's see if it's differentiable. The first condition we need to check is whether it's continuous or not. Is it? Why, yes it is. It checked out on all three conditions on the left side, so hence it must be continuous. So now that that's out of the way, I need to see whether the limit of the derivative on the left is the same as the limit of the derivative on the right. Pause the video again, see whether you think that's true. In this case, those two are not equal to each other. On the left side, because we have a constant slope of -1, that derivative is -1 on every value for when x is less than 0. On the right side, the value is +1. So for when x is greater than or equal to 0, the function value is always 1. Or the derivative is always 1, sorry. -1 is not the same as +1, so hence the limit of the derivative on the left is not the same as the limit of the derivative on the right. So, do I have enough information to answer my question now? Well, yes I do. F of x is not differentiable at x equals 0 because the limit as x approaches 0 on the left of f of prime of x is not the same as the limit as x approaches 0 on the right of the derivative. Notice how in my reason, I just cited the one thing that it failed, because that's all the information I needed. That's what told me that it wasn't differentiable, was that piece. So that was my reason after the because. That's how I justified my answer. Okay. So now I've applied my knowledge. Let's check if our answer is reasonable. Okay, some of you may have recognized already that because of the sharp turn in this absolute value function, we knew that it wasn't going to be differentiable. Okay, if any time a function has a sharp turn, the derivative is changing instantaneously. So hence the derivative at that point is not going to exist. Okay, so our answer is reasonable. Okay, so let's continue. We'll look at one more question. We're going to consider, I'm reading the question now according to Radar, that g of x is a piecewise defined function with x squared when x is less than 1, and it's defined as 2x plus 3 when x is greater than or equal to 1. We want to know, is g of x differentiable at x equals 1, and then justify our answer. Okay, so I've read the question. This next A is for ask, so I need to see what is it asking for. Just like in the last question, we say is it differentiable? So that's, again, my main idea, and I need to justify my answer. Same deal. Okay, I need to then also write down a sentence frame to help me know how to write my answer. Okay, so I remember to do all the pieces. So I want to say g of x, and leave a blank for is or is not, differentiable at x equals 1 because, and then I'll justify my answer. Okay, so I've written down that part. Let's decode now. So I have that little brace there tells me that this is a piecewise defined function. That's some good important information. Then the x equals 1 is where the function shifts, like it shifts from x squared to 2x plus 3 at x equal 1. Differentiable, again, is a key math word, and what does that tell us to do? If we want to know whether it's differentiable, I got to draw this table. I got to check all of those conditions to know whether it's true or not. Okay, and x equals 1 is the value that I'm interested in. All right, we've decoded. Let me walk you through one more time of how to determine whether this is continuous or differentiable or not. Okay, so does the function value exist at g of 1? Notice I haven't drawn a graph yet. We're just going to use the graph to check our answer, see if it's reasonable. But you can do this without having to draw a graph at all. So does the function value exist at g of 1? Pause and let me know. Okay, it does. when x equals 1, the piecewise function told us that that's the bottom function, so that's 2x plus 3. Plug in 1 for x, that would be equal to 5. Okay, I need to check the next condition. That is the limit as x approaches 1 from the left on g equals the limit as x approaches 1 from the right. What do you think? Nope, they're not the same. You'd want to make sure you showed your work separately. You can't just say that they're not equal. You need to find out what the values are so you can prove for sure they're not equal. So the limit as x approaches 1 from the left of g of x. On the left side, I'd be using the function x squared. So 1 squared would be 1. Okay. Then on the right, that's something we've already done. That would be the bottom function. I already plugged that in before. That's 2 times 1 plus 3. That gives me 5. Those two numbers are not equal. So because of differing behavior from left and right, I know that those two limits are not equal, and the limit itself does not exist, the overall limit. Okay, so what then can I conclude? Well, I already know now that g of x is not differentiable. Why? Because it's not continuous. So I would say because g is not continuous at x equals 1. Now, make my answer more complete, it would be best if I went ahead and put the reason why it's not continuous as well, and I can just cite the part of the test that it failed that we had in our table. Okay, so do I have to go through with the rest of it? Well, no, not really. Okay, let's check and see if our answer is reasonable though. So I'm going to graph it just to see what this function looks like now. I drew a dotted line at x equals 1 just because that's where the function is going to change. It's going to shift. Okay, so the left-hand side of x equals 1 is going to be the parabola x squared. So let me draw that in. Notice the open circle because we're not using that function at x equals 1. Then for 2x plus 3, on the other side, okay, we know it starts at the value of 5. Okay, y value of 5 when x equals 1, and it increases with a constant slope of 2. So like that, there's my function. Okay, so is it reasonable to say that g is not differentiable? Well, yeah, we can also see that g is not continuous at that point because of the jump discontinuity, and if it's not continuous, there's no way it can be differentiable. Okay, so it checks out as reasonable. We'll look at some examples of where it is differentiable in class, but just going with this. Hope you feel free to ask questions in class because I know that was a lot, and I'll see you guys then.